This is physical science, and this is the AM. I'm your host, Joe Shinga. Now, we're starting, the chemistry unit is big, so I've chunked it up, right? We started with balancing reactions and reaction types. Then we went into the mole concept. So mole conversions, grams to moles, moles to grams, is the most important out of all of these. Okay? The other one's the liters of gas is important. The grams per mole, though, way more important than this. Okay. So now we're going to do calculations involving balanced reactions. We will get to where we have to do all of those skills into one problem. So the first one I gave, I think you're familiar with this kind of problem. Now, this represents two hydrogens plus an oxygen molecule in water. I'm just putting this out here. Jot it down as one molecule at a time, but we will think of this as moles too. But just jot this down, and it's a real quick diagram, just to get this through our head. Okay? And I'll tell you more about it in a second. I'll pause the video. Okay, the reason why I want this is because I want you thinking along this line. Okay, in my diagram, this reaction represents two groups of hydrogen molecules, right? And one group, everything here is just green. Mixing with one group of oxygen, okay? Now, does it make sense then if I had, and I'll just change this number and I'll just put it above. If I had 20 groups, oh, I can't do this like the Norse ones, 20 groups of hydrogen, how many groups of oxygen with that 2-to-1 ratio would you need? 10, yeah. So it's a 2-to-1 ratio, 20 to 10. So then if I had 2 moles of hydrogen, too many to count, right? Okay, moles. If I had 2 moles of hydrogen, how many moles of oxygen? Or 2 to 1, I mean, over 2. It doesn't matter. It'd be like saying if I had 2 dozen, 24 hydrogen, right? I would need 1 dozen oxygen to mix with the one, like, to make the reaction. Dozens. Well, if I say moles, it works the same way. You need 2 moles of hydrogen to 1 mole of oxygen. You'll make 2 moles of water. So even though I think of this when I see it initially as molecules, singular, well, 2 molecules plus 1 mole, it's the same ratio for moles. We're going to use that throughout our calculations from pretty well now on. So you have a question here that I'm going to go through. How many moles of water are produced? How many moles of water produced when 0.867 moles of oxygen are reacted with? And I'm going to just say more than enough hydrogen. Okay? You don't have to be actually in a 2-to-1 ratio. We're not worried about that. So I'll say that extra hydrogen. That's not the issue. So here's how we set these up. It's going to be the same skill we've been using with grams and moles. Start with the single thing that's not a fraction. 0.867 moles of oxygen. Okay? We're not changing to grams. We don't need that in this question. Jot it down. So we want to find the moles of water. When I look at the reaction, you've got to look at the balanced reaction, and I balance. Oh, not hydrogen, oxygen. We've got 1 oxygen. There's no number you assume, it's a 1. The 2 waters made, right? For every 1 oxygen put in, you get 2 waters. So we're going to do that as a mathematical ratio. Now, it doesn't matter, like you said, if it's 1 oxygen or 1 mole of oxygen. same ratio. What do we want to get rid of? We want to get rid of the chemical oxygen. We're going to go with O2 on the bar. We want information about water. How many moles of water from the sample? We're going to put the H2O on the top. Then we look at the balanced reaction. We take the balancing front numbers, put them in. So that's 2 waters. I'm going to put in the 1. We didn't need the 1, but mathematically 1 doesn't change the bottom. But this is how we set it up. So math-wise, that's just multiply. And I'm not sure what it is exactly. Somebody 1.7 something or other. So is it 1.73? No? Yes. Let's do times 2, right? And we cut it off, it's 173.4, but we correctly heard right off the bat the right number of digits because it's 3 digits in. The 2 to 1 ratio for balancing in the brackets, that's infinitely correct. Don't use that to make decisions. So then I say, well, what are my units? I've gotten rid of oxygen. Now I have moles of water produced. Okay? Yes. It is, and you don't have to rewrite moles because it's actually the same ratio, like I said, for molecules. One little itty bitty oxygen molecule is actually isolated to 2 molecules of water. And it's the same for moles. As long as we're talking, it's also the same for dozens and stuff like that. So we don't have to put the MOL in moles. Okay. Based on the same equation, then you have another one. Oh, the reason why there's a star there is because I've done this problem before. I have to say, like, figure 1. So 0.533 moles of water are made. So we're working backwards on this one. Another 0.5 there, like on the wrong number. 3 moles water, H2O. So I want to get rid of information about water, and I want to get to moles of hydrogen. That's H2. And I look at the balanced reaction, and the front number is the balancing number. And I see that it's a 2 to 2. I'm going to write it down as 2 to 2. I think you understand something. I don't need to put this in my calculator. Why not? Yeah, it's 2 divided by 2. Yeah. So, but mathematically, I've shown what it works. Right? I've gotten rid of the water, and that the number of moles of hydrogen used is the exact same. You could put it in your calculator. I'm fine with it. Sometimes you just kind of do because you kind of in an automatic robot mode where you're not really thinking. Yeah. 2 divided by 2. Okay. Well then I've got another thing to try. There we go. Got the flip side. This one. Hydrogen plus nitrogen makes ammonium. Ammonium. When we were naming molecules and stuff like this, I think I told you this one's not as common. We use a naming system for most molecules, except for water, and everybody knows water, and ammonia. Ammonia I'll keep in mind. That's the stuff in Windex glass. It smells really good. Okay. Same kind of question, so I'm not going to go over the whole thing that's, well, I guess energy. It gives off energy when it's hot. So that doesn't affect your grams or your moles. We're going to come back to that energy thing. Sometimes I'll just put it in there just to get you used to this idea. And we'll actually have numbers for the energy by the end of the semester. Anyways, find the moles of ammonia. Given that 3.6 moles of hydrogen is reactive. So 3.6 moles of hydrogen. Yeah. So you do the same skill that we've been doing in grams and moles. I want to get rid of information of hydrogen, about hydrogen. I want information about NH3. I look up the balance numbers. There's 2 NH3s for every 3 hydrogen. So times 3 divided by 2 is what I'm going to do. 3.6 times 3 divided by 2. Oh, I said it backwards. Oh, times 2 divided by 3. I get 2.4. Should be small. 2.4. I'm going to put 2.4 down. There's no extra digits. It's 2 digits. And it is moles, got rid of these, of ammonia. Okay? First, we're going to have some practice. So we'll go through this, and I put B down twice. Not that that's a huge deal, but I'll just change this. I don't think you're too confused. Let's see. Okay. Find the moles of ammonia given that 19.6 moles of nitrogen. Well, same skills. 19.6. Now we got 3 digits. Moles of nitrogen gas. I want to get rid of information about nitrogen gas. I want ammonia involved. I re-look at the balance reaction. I see that nitrogen is 1. You don't have to put down the 1 because it mathematically doesn't. It's assumed. So I'm really going 19.6 times 39 decimals. Keeping those digits and moles, rid of nitrogen, of ammonia. There we go. Last thing. Find the moles of hydrogen. Given that there was 1.2 moles of nitrogen. Well, I want to get rid of nitrogen. Have information about hydrogen. Again, nitrogen is a 1 from the balance reaction. If we look up, 3 for hydrogen. It's 1.2 times 3. 36, moles. Here we are. Okay. That's some time. We're cracked. Are there any questions before we start?